so we finally know what LP spaces are as of last lecture. So those are, so a Banach space is a complete normed space. The LP spaces are, you take the normed space, which is f is either R or C. You take f-valued functions on x. X is an integral pair. From that, you can define the p norm for any p between 1 and infinity, and that's a normed space. You take its completion. Well, in the case p equals infinity, that's redundant because it's already complete. Otherwise, it's not. So you take the completion. That's the LP space. So by definition, vectors in this vector space are Cauchy sequences of continuous f-valued functions on x, Cauchy with respect to the dp metric. So that's some complete normed space. The question I want to answer in today's lecture is, well, why do people care about these spaces? What's so special about them? I'll hope to get to the point of stating the duality theorem, which explains why they're special. But before that, we need to talk about bounded linear operators and operator norms. Okay, so I stated the lemma that you see there and sketched its proof. So this was the universal property of the completion of a metric space. Let me remind you. So I start with a metric space. This is a complete metric space. This is the inclusion of the space into its completion as constant sequences. And I said that any uniformly continuous f has a unique lift. That is, there's a unique continuous map, capital F, out of the completion, which restricts to lowercase f. Moreover, that unique continuous extension is itself uniformly continuous. Okay, and it can be computed. Right, so from now on, when we think about a point of the completion, just think about it. I mean, it's a Cauchy sequence, but it's actually more convenient to think about it as just being a limit of a sequence of things that live in the subset X. Right, identify X with a subset of X hat. So any X that comes as a limit of things in X, the value of capital F on that is just computed by evaluating lowercase f on all the things in the sequence and taking the limit in Y. All right, so I sketched the proof of that, so we take that as given. Now I want to explain the analogous statement for norm spaces. Right. So I'm going to use this exercise. I'm going to prove a more general form of that later in the lecture. So anyway, this is fine. So it says that if they're norm spaces and I have a linear map between them, then continuity is the same as uniform continuity. Well, you can believe that because if you remember when we discussed topological abelian groups, somehow everything important happens at the origin in a topological group. So well, if I can make something continuous at the origin, then it works everywhere. So that's sort of a clear argument for uniform continuity versus continuity. Again, I'll explain the formal version of what I just said in a minute. All right, so given this statement, let's now argue for the theorem. So take a normed space and a Banach space. So we know how to complete the normed space. So first complete it as a metric space, and then there's a natural norm on that. So remember that recall that if V is a point in the completion, let's say V is obtained as a limit of things in V, uppercase V, then the norm of V in V hat is by definition the limit of the norms of all the things converging to it in lowercase v. All right, so that makes V hat into a norm space. This is a norm-preserving injective linear map from V to V hat. Let me take a continuous and linear map out of the normed space. Okay, so there's no linearity over there. That's just metric spaces and continuity. But here I'm saying continuous and linear. Well, by the exercise, continuous and linear means uniformly continuous. All right, so then just using the original picture, right? Lying behind this picture is the same picture, but for the metric spaces. That's a metric space. That's a complete metric space. That's a complete metric space, because I said Banach. So just looking at the lemma, that tells me immediately that there's a unique, well, it's unique as a continuous map, but it's also unique as a uniformly continuous map. F from V hat to W, which restricts on V to lowercase f. So the uniqueness in the statement is taken care of. All I need to do is to prove that this resulting capital F is linear, and I'm done. Okay. So how do I show that this F is linear? Well, it's linear when I restrict it to V, right? Because there it's lowercase f, and lowercase f is linear. So I basically need to show something like, if your map is linear on a dense subset, then it's linear everywhere. All right. But note that f is linear if and only if the following diagrams commute. What does that diagram say? To say that diagram, so there's two of them, maybe I'll draw both and then explain. Right, so I claim that F is linear if and only if those two diagrams commute. Well, why is that? What does it say? What does it mean to say this diagram commutes? It means if I take any element here and run around this way in the diagram, I get the same element of W as running around that way. And what does that do? If I feed in VV prime, going this way gives me, this is the sum map, that's V plus V prime. And then going to here is F of V plus V prime. Going the other way, I apply F cross F, that gives me the pair FV FV prime, and then down here gives me F of V plus F of V prime. Okay, so the two ways around the diagram are exactly the two things I need to show are equal in order to show that it's a morphism of abelian groups. Again, similarly here, a pair lambda V, one way around the diagram will give you F of lambda V, and the other way will give you lambda of F V. Okay, so if I can show those two diagrams commute, then I'm done. I've showed that F is linear. All right, so next I have to observe that every map in those diagrams is continuous. A normed space is a topological vector space with respect to its addition and scalar multiplication. Right? So that's continuous, that's continuous, that's continuous, that's continuous. F is by construction continuous, so these two things are continuous. All right, so everything is continuous. Okay, but if I want to show two continuous maps are equal, for instance, that continuous map, the composite, and that continuous map, if I want to show they're equal, I just need to show they're equal on a dense subset. So these comparisons are of continuous maps out of V hat V, respectively R cross V hat, which agree on V cross V and R cross V. All right, maybe I'll just fill in the details for the first check. So to show the two ways around that diagram are equal, so V cross V sits inside V hat cross V hat. V is dense in V hat, and then it's an easy exercise to see that the product of two dense subsets is dense. So that is a dense subset of this. So if I have two continuous maps out of a topological space to a Hausdorff space, and they agree on a dense subset, then they agree. So I just need to show that blah, blah, blah is equal to blah, blah, blah. But that's true, because restricting F to V is just lowercase f. And lowercase f is linear. So this composite is lowercase f of v plus lowercase f of v prime. And this composite is lowercase f of v plus v prime, which are equal, because f is linear. Similarly for the other diagram. So both of the ways around those two diagrams agree on a dense subset and therefore are equal. So So I'm done. So any linear continuous map out of V has a unique extension to a continuous linear map out of V hat. Any questions about that argument? Okay. All right, so what's so special about LP spaces? Well, I claim they are as close as finite dimensional, as close to being something like finite dimensional as you can find within the world of infinite dimensional spaces. Okay, that seems like a bit of a strange statement, but so remember that as soon as X is not a finite set of points, this space is infinite dimensional, and it sits as a subspace in this, so this is certainly infinite dimensional. Okay, so these are not finite dimensional vector spaces. But there's a sense in which they're nonetheless finite, and that's what I want to explain. Okay, well, they're certainly not finite dimensional, so this word finite certainly has to mean something else. So what I'm going to do is start by characterizing, in the case of vector spaces over a field, I mean, there's many ways of saying finite dimensional, so many conditions which are equivalent for vector spaces to being finite dimensional. So I want to state some of those conditions, and some of the other conditions, which don't say a finite basis, those things generalize, and that's the sense in which this is finite. Okay, so let K be a field, and V a vector space over K. Then the following are equivalent. V is finite dimensional. Two, the canonical map, let's call it delta. So remember, star means the linear dual, so that's the space of all linear maps from V to K. So we do it twice, that's some vector space. There's a canonical map from V to V double dual, which sends a vector W to the function of functions, which sends a function to its value at W. Okay. So delta W needs to be a vector here, which is to say it needs to be a linear transformation from V star to K. Well, what does this linear transformation do? It eats a linear transformation from V to K, call it W, sorry, call it F, and it outputs a number which is the value of F at W. Okay, so that's what delta is. And the condition is that that's an isomorphism of vector spaces. All right, so that's one condition. That pre-existing map is an isomorphism. And thirdly, there exists an isomorphism between V and its dual as vector spaces. There's no canonical map even between those in either direction. So what I'm saying here is that there just exists some abstract isomorphism between those two vector spaces. All right, so those are three conditions, and I claim they're equivalent. The equivalence between the first two, so I'm not going to give the proof, so for two reasons. One, so in the tutorial this week we'll discuss the necessary background on bases which are required to even understand this proof. And secondly, it's sort of a little orthogonal to what I want to get to in the lecture, so I'm going to skip the proof, but it's in the notes, at least the proof of the first two being equivalent. All right, the third one, I mean, this is hard. Seems like a simple statement. This is not easy to see that that is equivalent to the other two. And we're only going to use it in order to inform the discussion, so it's not really foundational to what we're going to do later. So I need it to tell the story, but it's not so important from the point of view of the proof. Okay, so there we've got two conditions. So we've got this guy and this guy, which give us another way of saying what it means for a vector space to be finite dimensional. Okay, so for an infinite dimensional space, so we're going to restrict to the real numbers simply to avoid some complications with conjugates of vector spaces that I'll deal with later. So for an infinite dimensional vector space like this, or like the LP space, well, you should read this as sort of saying that the linear dual is not a very good object. That is, the ordinary dual, the star, that is not a good object for infinite dimensional vector spaces. It's a sort of not necessarily going to be of any use. But there's an obvious candidate reason for why that's not a reasonable notion of dual in this case, right? Because if I'm going to form the dual of one of these spaces, let's say this, I mean, that's a vector space over R. This makes sense, right? That's a vector space. So is this. So what is that vector space? That's all linear maps from this space to R. But there's more structure on the domain of such maps than just the vector space structure. There's also the topology, right? These are topological vector spaces. So just looking at maps which preserve the linear structure is a bit strange, right? I mean, maybe the more natural thing to write down would be the set of all maps from here to here which preserve all the structure, namely the topology and the linear structure. Okay, and then you might guess that it's the fact that we chose the wrong notion of dual, the naive notion of dual, which ignored structure, which leads to the fact that these spaces don't look very well behaved from the point of view of duals. And in fact, that's the case. So that's what I want to explain. What's the right notion? Okay, let's stick to R. Okay, so if we take a topological vector space over R, then we can consider two notions of dual. One is V star, just linear maps, and the other one, which I'm going to note V check, or alternatively by this notation, is, as I hope the notation suggests, continuous linear maps from V to R. So at the moment, those are just sets. Okay, the first observation is that in the finite dimensional case, these are the same thing. Well, obviously there's another thing I could put here, which is just continuous maps from V to R, but that's not really a dual in the sense of linear algebra, right? So I don't talk about that. Okay, so the set of continuous linear maps certainly sits within the set of linear maps. I claim that if the dimension of V is finite and V is Hausdorff, so the way I've defined it, a topological vector space doesn't have to be Hausdorff as a topological space. It is if and only if any point is closed, in particular if the zero is closed. Okay, so that's sort of a technical thing. All the topological vector spaces we care about are Hausdorff. So if it's finite dimensional, then every linear map is continuous. Why? Well, the argument is, you know, one way of making a finite dimensional vector space into a topological vector space, which is just choose a basis. A basis gives you a linear isomorphism with Rn. Just take the topology there and move it over. That gives a topological structure to V. And actually you can see that is the only way of getting a Hausdorff topological structure on a vector space. So in this case, I mean, there was an exercise earlier in the notes which asked you to show that any linear map, if I put, any linear map like this with the usual topology on Rn is continuous, right? Because it's a matrix, so it's a continuous map. And therefore, if the topological structure on this comes from such a bijection, any linear map from V to R is also continuous. And since that's the only way of putting a structure on V like that, that shows you that this equality is the case. Okay, so these two notions of dual coincide for finite dimensional topological vector spaces. So there's no point really in considering this notion of dual. All right, but this in general, that's not the case. All right. So the imposition of the condition of continuity is a real restriction. It picks out a smaller set of linear maps from V to R. Okay, so now the question is, so this is maybe what you might think is the reasonable notion of a dual for a topological vector space. Well, what topological vector spaces do we know that aren't finite dimensional? The first ones we run into naturally are function spaces. Okay, so the natural question is, what is LP XR check? Okay, so this thing is called the continuous linear dual. I could say, anyway, so. Okay, so those are natural questions. Take the topological vector space, take its dual, what is that? In this case, there's actually a question mark, right? Which is, what do I mean? To make sense of this, I need a topology and a vector space structure on this thing. It's clear what the vector space structure is. That's never changed. Yeah.
Is that a V or is it an upside down?
Yeah, it's an upside down hat. Yeah, I agree. V to the V. I don't know how to make that look any less like a V. Maybe it needs to be flat.
And following that, why is it called check? Also logical or is it just false?
I don't know.
Why is anything called anything?
Why is it a check?
I don't know how you would just call it.
I don't know the answer to that question. It looks like a check mark, I guess. I don't know. That's about as good as I can do. All right. So if we're going to make sense of the check, well, I need to decide what topology I'm putting on that space, right? But I've got choices. Right, for every P, I've got a norm, and that gives a topology, which makes that a topological vector space. So this is not really well-defined notation. It depends on the choice of the P. Once I've chosen a P, that becomes a normed vector space with this norm, therefore topological vector space, therefore I can ask this question. But actually, if I choose P as my norm to make sense of the topology there, this is actually the same thing as that. Because taking the dual completions don't see the dual doesn't see the difference between a normed space and its completion. Okay, so actually the only question is this one. Okay, so what is the dual of an LP space? Okay, so to answer that question, it's convenient to first of all, well, this is a somewhat specialized question, right? I started by talking about duals, continuous linear duals of arbitrary topological vector spaces. But this question is not about arbitrary topological vector spaces, it's about normed vector spaces. That's actually an easier context, so I'm going to stick to that. So we're just going to think about the continuous linear dual of a normed space, for example, that one. And for that purpose, it's convenient to introduce the following notions. Okay, so the point is that a linear map out of a normed space is continuous if and only if it's bounded. I'll prove that in a second. And that's sort of more convenient than continuity. So what does bounded mean? Well, it means what you expect from what we've been discussing with functions. So think about this as boundedness of the set. Well, right, the ratio of the length of t of v with respect to the length of the original vector, if that ratio is bounded, then we call the operator, or the linear map. Yeah, for some reason we start saying the word operator. Okay, operator just means linear transformation, linear map. But when we talk about normed spaces, we often say the word operator. Okay, that's a synonym. So if that set is bounded, it's certainly bounded below by 0, because those are all positive. But if it's bounded above, which is the same thing as to say there exists an M satisfying that, then we call the operator bounded. Yeah.
So is the F in the definition meant to be?
Oh, thank you. Yeah. And we also start writing T. Operators are T and S and U. All right. So thanks. Yeah. So it's bounded if there exists an M satisfying that. And then the norm of the operator is defined to be the supremum of, well, the following equivalent supremum. Okay, so take that set which was bounded above, take its supremum. That's some number. So this is, so if T is bounded, the operator norm of T is the supremum of that set. And if you think about it, you'll see that this number is the least M for which this works for all V. So it's the infimum of those M for which, let's call it star, holds. Okay, so that's some number. That's the norm of the operator. I mean, if you look at that expression, you can see it's connected to the eigenvalues, right? We'll maybe discuss that later. Okay. In particular, we have that this. Right? The norm was the least m for which it works, but since it's an infimum and inequalities work with infimums, maybe that's not a very precise statement. I mean, we've done a few calculations in the last few lectures where I had some thing satisfying an inequality, which was parameterized by an integer n. Then I went to the limit and it was still satisfying the inequality, right? So for the same reason, this is true. Okay, so I actually have this inequality with respect to the operator norm of t for all v. Okay, so theorem. As I've already advertised, if I have a linear operator between normed spaces, the following conditions are equivalent. T is continuous. Well, let me state them in the order of their implications. So T is bounded. T is uniformly continuous. 3, what? T is continuous. 4, T is continuous at 0. Okay, so if I want to consider the continuous linear dual of a normed space, I'm actually talking about bounded operators. That's the point. Okay, so let's prove the theorem. Well, I hope at least the first implication, 1 to 2, is fairly clear. Right, because I mean, remember, continuity is with respect to the induced metric from the norm. So the distance between TV and TW in W is the norm of the difference. So this is the quantity I have to bound in order to prove that something is uniformly continuous. But that thing, by linearity, is equal to T of V minus W. And then I can use that inequality. So that's less than or equal to the norm of T times V minus W. But that's the distance in V between V and W, right? So that shows you it's uniformly continuous, because given epsilon, if you want to make this less than epsilon, you just have to make this less than epsilon divided by the norm of T. Notice the norm of T can't be 0, right? It's a supremum of things that are actually positive. Okay, well, maybe I shouldn't have said that. I mean, it could be the 0 map, right? But then that's continuous, so no problem. Okay, so that shows uniformly continuous. Well, that's for free. That's for free. Okay, so I just need to prove that if it's continuous at 0 in V, then it's bounded. What does it mean to say that it's continuous at 0? It means that given epsilon greater than 0, we can find a delta such that if the distance of something to 0 in v, let's say, so v minus 0, it's just v, if that's less than that, and that implies the distance between t of v and t of 0, which is 0, is less than epsilon. Okay, so then I just mangle that a little, and I'll find an upper bound for things like this in terms of something multiplied by the norm of v, and I'll have to check the precise mangling. Right, so I mean we don't need to use all epsilons because we just need to produce an upper bound, so we might as well just take epsilon to be 1. Okay, I mean it's still true. Okay, so then for v not equal to 0, okay, so v is not 0, so take this number, this is the delta produced for epsilon equals 1, divided by 2 times the length of v, that's a number, multiply it by v, take the norm. If you take this part out and cancel out the norm of v, then you get this, that's less than delta. So that tells you that the norm of t of all of that, w, must be less than 1. Well, t is linear, so this number comes out the front, and then the absolute value of it, which is just a number because it's positive, comes out the front of the norm. And moving it over the other side, you'll find t of v w is less than 2 on delta that. Well, that's enough, right? There's your m. And it worked for all v, right? The delta and the v had nothing to do with one another. So the delta works for all v. Okay, so therefore t is bound. Okay. Questions about that argument? All right. So that tells us that if we want to talk about the continuous linear dual of a normed space, it's the same to talk about bounded linear operators from that space to the field. Okay, so V is a normed space. Continuous linear maps from V to R, and here you're using, well, the topology which comes from the norm. By what we've just shown, that's all the t's from V to R such that t is linear and bounded. Okay, so exercise. Well, so far V check. So far V check has just been a set, right? It was just a set of continuous linear maps from V to R. It's clearly a vector space because I can add continuous maps and they're continuous, and I can add linear maps and they're linear. Okay, so that's a vector space with the natural operations. But I claim it's also, the natural topology on it comes from a norm, and the norm is the one I've just defined, right? Because anything in here is bounded, so that means I can take its norm, that's a number, and I claim that the pair consisting of this vector space together with the operator norm is not just a normed space, it's actually also complete. Okay, so that's a Banach space. All right. Right, so this is our question, right? Take this normed space for some p, compute its linear dual. Well, now we know continuous linear dual. Now we know how to think about this actually as a normed space. Right. Okay, so if I give you a p between 1 and infinity, there's a unique solution to that equation q, right? So q is p on p minus 1. I mean, the way to think about that is there's a bijection between the interval 1 infinity and the interval 0 to 1. So just map p to 1 on p and then take the other part of the interval. That's the 1 on q. Right, so that's a bijection. The joule of p is p again, right? Because that's symmetric in p and q. So that's a sort of involution on the set of p's between 1 and infinity. Okay, so the claim is that this is LQ. So if that doesn't blow your mind, there's something wrong with your mind. Okay, so this is a very beautiful fact. Also, why would you believe something like that? How could we arrive at that kind of statement? Well, what is it saying? It's saying that, in particular, it's saying that if I take anything in LQ, so that's a Cauchy sequence, but whatever, just think about it as a real valued function on X, and I'm supposed to define a functional on real valued functions on X, that is the left-hand side. So I need to take a function and get a gadget which takes a function and gives me a number. Well, there's only really one kind of thing that does that, and that's the integral. Right? Take a function, take another function, get a number. Right, so I claim this formula is what's behind that isomorphism. So that'll take some explanation. That's what's going on. Okay, so claim. I've done it the other way around in the notes, I'm sorry. Okay, well, if I want to connect the LP spaces, those are completions of things, so I might as well try and connect the things of which they are completions. Right, so I do that first. So take X, so X is as usual an integral pair. Take the Q norm. So for the rest of the lecture, P and Q are dual exponents in the sense I defined. So take the Q norm on this space and the P norm on the same space, and then take the dual space, the continuous linear dual of that normed space. All right, so I claim I've got a continuous linear map between those two normed spaces, given by sending G to, let's call it LG. So LG, what's wrong with LG? You guys are full of complaints about notation today. You're going to ask why L? Because I multiplied on the left. Okay, fine. I. Is that okay? It's an integral. All right. Yeah. Okay. So that's a formula, right? So okay, so let's agree this is well defined, right? Because G is a continuous map on X, so is F. I multiply them, it's still continuous. I can integrate it, I get a number. Okay, so that's a well-defined function from here to R. All right, so IG is linear. Well, the first check I need to do is that IG actually lives in the right-hand side, right? That is, I need to check it's actually a bounded linear map from there to there, where I put the P norm on this side. Okay, so that's the first check I need to do, that that's bounded and linear. All right, and that follows from Holder's inequality, which we sort of skipped, but it followed from the same sort of yoga as the check that this was a norm. Well, linearity is clear. The integral is linear, so I need to only convince you about boundedness. So what would it mean to check that this thing is bounded? Well, I'd need to take the norm of IG of F, and I'd need to somehow get to an inequality with some number m times the norm of F with respect to the norm I'm putting on the domain, which is P. Okay, so that's what I've got to do. So that's the norm of the integral of GF, which is less than or equal to the integral of GF. But that's by definition the one norm of the product, and Holder's inequality tells that for dual exponents, this is less than or equal to that product. So this is this number. Right, so I'm done. So IG is bounded. And in fact, its norm, its operator norm, is less than or equal to the norm of G. In fact, that's equal, but I won't have time to prove that. Okay, so this map is continuous. It's bounded and linear, therefore continuous and linear, so it's an element of the right-hand side. This map here, by the same calculation, is not only linear in G, but also bounded. So this is therefore a continuous linear map between these two normed spaces. Okay. So what have I got? Right, so let's worry about the left-hand side first. So this is a normed space, that's its completion. This is the canonical map which sits inside the completion. No problem. I also have the same map. Maybe I should put subscripts. I've got the same map for P. Forget the checks. So the same map for P would sit this guy inside LP. Check is contravariant, so to speak. So when you apply the dual, right, as we discussed in the tutorial, the dual of a linear transformation is a linear transformation back the other way between the duals. So it's the same here. So this is a continuous linear map of normed spaces, and it's actually an isomorphism. Maybe that seems surprising, but that's just the content of this statement about unique lifting of continuous linear maps from a normed space to its completion. That says precisely that that's an isomorphism if you think about it. Okay, so this is an isomorphism. So what I can do is I can take this map, which is, if you like, L blank, right? So that's the map. G goes to LG, so put the G in there. So that map is continuous and linear. That's what I just checked by checking it was bounded. This is an isomorphism of normed spaces. So take its inverse. So that's continuous and linear, that's continuous and linear. So the composite is continuous and linear. And by the universal property of the completion, which we just discussed, there's a unique continuous linear map, which we'll call phi QP, right, from Q to P. The theorem says this is an isomorphism of Banach spaces. Okay, so I'm going to prove this theorem in the special case P equals 2, therefore Q equals 2 later. But all right, so this suffices for me to explain finally what the point is of the LP spaces. Okay, so let me compute. LQ XR is isomorphic to the dual of LP. But I can read this in the opposite order, right? LP is isomorphic to the dual of LQ because the relation of being exponent is symmetric. Okay, so that means I can put LQ dual inside that dual. So that's LQ dual. Well, this is what I started the lecture with, right? A finite dimensional vector space is something which is the canonical map. In fact, this is the canonical map, although it's a little hidden that that's the case. The canonical map from this Banach space to its double dual is actually an isomorphism of Banach spaces. Right. So it's infinite dimensional, so it's not isomorphic to double star of itself. But if I use the right dual, namely the continuous linear dual, it is. Right. So in that sense, this Banach space is a finite dimensional object in a sense, but where we use this alternative characterization and swapped in the continuous linear dual. And finally, if I put P equals 2, then Q equals 2. So this isomorphism in the theorem gives me that L2 is self-dual. Well, that was the other characterization of finite dimensionality, right? So in the infinite dimensional case, these conditions, which were equivalent, right, being isomorphic to the double linear dual and being isomorphic to the single linear dual, were equivalent for vector spaces and characterized finite dimensionality. In this case, they're disjoint conditions, and this is weaker. So all the LP spaces are isomorphic to their double dual, but only L2 is on the nose isomorphic to its own dual. And that's the sense in which it's the most finite kind of Banach space. All right. So I'm over time, but this was where I wanted to get to. A self-dual Banach space is what's called a Hilbert space. That's what Hilbert spaces are. All right, thanks guys. The assignments are up the front as well.